quick look at some amine spectroscopy. IR is going to be very important for us in identifying amines, because if we look up above 3000 here, if we see some sort of spikes up here, that's good evidence that there's an NH in the molecule. And if there's two spikes right next to each other, that's an NH2, right? So literally the number of spikes tells us the number of H's that's attached to the N, because what we're seeing right there is really a stretching of the NH bond itself. And if there's two of them, there's two different frequencies that they can be stretching at. So if you see those two spikes, that's an NH2. If you see just one spike over there, that's an NH. In NMR, the NH is exchangeable. So if we do see it at all, it's sort of broadened and it disappears if we add D2O. If we add some heavy water to our sample, that NH will be replaced with an ND, which does not show up. So same thing we said with alcohols. The broadened OH peak can disappear with D2O. If we have an N-methyl, that's a distinctive 3-hydrogen singlet that'll be around 2.5. So it's a little further downfield than the methyl ketone. Remember, we said that's a 3H singlet at around 2, so 2.5 or so is an indication of a N-methyl group. That's really about all unique things that we can tell by NMR. Of course, everything we already have learned about triplets and doublets and singlets and so on still apply. MS, mass spectrometry, is very useful for identifying amines. Way back in the MS chapter, I told you the nitrogen rule is that a compound will have an odd massed molecular ion if there's an odd number of nitrogens, right? That molecular ion is just the molecular weight, essentially. It's the highest mass peak. The peak that's furthest to the right on the mass spec. That's the molecular ion. If that's odd, we've got probably 1 or 3 nitrogens in our compound. If it's even, we don't know anything about nitrogens. Amines will fragment themselves by alpha cleavage, which, remember, if we look at our N, right, that's right here, and if I find the CC bond that's closest to that N, right, fragment of that is alpha cleavage, and that leaves a carbocation next to the N, which is resonance stabilized. So that's why alpha cleavage is so important. It makes the stable carbocation, which will show up at very high abundance in mass spec. So look at this ethyl propyl amine, right? What we have here is 87 is the molecular ion. That's consistent with there being 1 nitrogen, or an odd number of nitrogens in the compound. 2 opportunities for alpha cleavage here. The one over on the left here will remove a methyl group, so that's 87 minus 15. The one over here removes an ethyl group. That's 87 minus 29. Okay, and if you want to draw the plus charge on the N, you can, or you can just make the plus as part of the molecule. But of course, the other resonance structure is a carbocation, H2C plus NH, CH2, CH2, CH3. So there's alpha cleavage. So be familiar with alpha cleavage, be able to identify the main peaks from alpha cleavage that come from breaking the CC bond nearest the nitrogen. So I think that's it for this chapter.